Okay, so we've talked about what you need to do if they ask you to graphically verify, but sometimes it's not always easy to know exactly what you're plotting. So what do we plot? Well, we need to plot the variables, right? The variable quantities, and our slope and y-intercept should be constants. Now, you will recall that the equation of a straight line is y equals mx plus b. Y is a variable because there's going to be multiple values. X is a variable, there's multiple values. The slope and the intercept, well, they're single valued, constants in other words. In the previous problem, we had the formula F equals ma, where this m is the mass of the card. Now, we had multiple measurements of F and multiple measurements of A, and we only have one card, so it only has the one mass. So it makes sense that we would plot F on the y-axis and the acceleration on the x-axis. So then our mass, the mass of the cart, will be the same as the slope. Our intercept b, why, that's got to be 0. So b is going to be 0. Now that we know that the mass is the same as the slope, we also know that the uncertainty in our measurement of the mass is the same as the uncertainty in the slope. Okay, here's another example, slightly more complicated than the one we had before. It says pressure increases with increasing depth according to the formula P equals P naught plus rho GD, where P naught is the pressure at the surface, rho is the density of the fluid, G is is gravity in feet per second squared, we're definitely not SI, and D is the depth. It says measure the pressure at different depths of water. Determine the surface pressure, a constant, and the density of the water, also a constant. Great. So, again, we start with the equation of our line, which is y equals mx plus b. And we write our equation underneath. P. Now, P naught's a constant, so I'll put it over on this side, equals rho GD plus P naught. It should be clear, since pressure varies, we will plot that on the y-axis. The depth varies, we'll plot that on the x-axis. Our y-intercept is going to be the quantity P naught, the surface pressure. And our slope is more complicated than usual. It's going to be rho times G. So, as a result, we have rho G equal to the slope, or that's the same as saying that rho equals m over G. The uncertainty in rho, using our uncertainty propagation formulas, will be rho delta m over m plus delta G over G. And our value of the surface pressure is just equal to the intercept, and delta P naught, the uncertainty in that measurement, is just whatever we had for the uncertainty of the y-intercept. Okay, another example. It says the density of alcohol obeys the formula D equals m over V, where D is the density, m is the mass of the alcohol, and V is the volume. Place a graduated cylinder on a weigh scale and zero the scale. Okay, so anything you add now will just be the weight of the added material. Now we add the various amounts of alcohol and record the mass from the scale and the volume from the side of the graduated cylinder, which is marked, usually in milliliters. Find the density of the alcohol and compare it to the accepted value of ... whatever that is. We don't really care. Now again, the equation of a line is mx plus b. But now we've got a bit of a problem here. Our variables are m and v, and they're on the same side of the equation. Y and x are on different sides of the equation. So we need to rearrange this formula such that each variable is on one side of the equal sign. Well, that's easy to do. We just cross multiply. We say that m equals dv plus 0 if you'd like. Okay? So all I did was rewrite the formula so that one variable could be put on the x-axis and the second variable could be put on the x-axis. Our intercept will be 0, and the density of the material is determined simply by the slope. So d equals m, delta d equals delta m. We get the uncertainty in our measurement of the density of alcohol from the uncertainty of the slope. Just to point out again, the variables have to be on opposite sides of the equal signs. If they're not, you must rearrange the formula. Okay. Here's our last example. It's an example of a nonlinear equation. It says a cart with a fixed initial speed v0 is allowed to travel different distances d down an inclined plane. And the final velocity d at the end of that distance is measured. Kinematics gives us the equation that v squared equals v0 squared plus 2ad. Graphically verify the above equation and determine the initial velocity and the acceleration a. So the initial velocity is a constant. The acceleration is a constant. Okay? V and d are our variables, but v is squared. We write down our equation of the straight line again, and we write our equation underneath. And as usual, the constant term I write at the end. And what we have to plot on the y-axis is not v, but v squared. If we plot v, it's going to be a curve, not a straight line. So we always have to make sure we plot the correct thing. You'll be measuring v, but then you'll have to square each of your terms. Okay, so on the x-axis, we're going to plot the different distances d. So we're going to find that v0 squared is equal to the intercept, or v0 is equal to the square root of the intercept. And in terms of the uncertainties, and using uncertainty propagation, 2v0 delta v0 equals delta b, or delta v0 is delta b over 2v0. We also find that 2a is equal to the slope, or a equals 1/2 of m, and delta a is 1/2 delta m. Okay? So from the graph, we can in fact get the initial velocity and the acceleration. We just had to be careful that when quantities are squared or cubed or square rooted, that we plot those quantities to get the straight line. Thank you.